and then under tools select the board as Arduino Uno and port that same port so you can upload your program. Once you upload, you should get something like this. You can get it once using the void setup function here, or like continuously using the void loop function. So this much only. Any question? If no question, stop. So my demo is over.
Before we start demo with Sunil, anyone has any question to Gargi? Okay. Okay, Sunil, you can start.
Yeah, good morning to all. I'm sharing my screen. Please just confirm that it is visible or not. Is my screen visible to you? Better one.
Yes, sir.
Yeah, it is visible. Yeah.
Okay, okay. So before starting, let me play a small video so that you all can get that today in this class what we are going to learn. So in today's class, we are going to see how we are measuring current non-invasively, how we are sampling it, and how we are getting the fast Fourier transform or that Fourier transform on a Raspberry Pi platform. So all this we will be seeing in our this PPT. You just for just overview, I am playing this video so that you all can get idea. Okay, so good morning class. Myself Sunil Pradhan. I am senior research fellow in department of IIT Kharagpur. So starting with whatever we will be learning in the class. Slideshow. So today, first we will be seeing that how a current sensor is interfaced to a Raspberry Pi by a ADC, and in that series, how we are conditioning the circuit, how we are conditioning the signal with the signal conditioning circuit, and why do we need it? What all noise we are getting, and to remove that noise, we are using a low pass filter. And once the signal it is arriving to a ADC, how we can choose that which ADC will be perfect for us, that ADC interfacing to a Raspberry Pi. And once that all is interface. Now we have to just get the data from the ADC to our Pi. What are the different techniques and different methods? And at last, we will be analyzing the signals, that data we got, and we'll try to find the Fourier transform. Apart from Fourier transform, we are having lot of tools, but we will be keeping it confined in this lecture. So this is my the wiring diagram, or you can take it as an overview also. I can tell that it is a wiring diagram, or this is my this overview PPT. Here you can see that this is a current sensor. Before starting, let me tell you that after this lecture, you will be given an assignment. So just listen it carefully, like what sensors I am using and how I am choosing my ADC, and what are all there in my the signal conditioning circuit. So this is a current sensor. First it will be sensing, and this is my wire in which current is flowing. So non-invasively it is sensing my current. So assume that if a current is well, this is my current waveform. If I'm directly sensing this my signal from this current sensor, I will be getting a lot of noise. All that noise I will be showing you in the later stage. So that noise and I need only this signal. I don't want this noise, so I have to filter all this. So to filter all this, I need a signal conditioning circuit. So once I'm passing this signal through my current this signal conditioning circuit, I will be getting a smooth sine curve. This is my current signal, not this one, because here I'm having lot of noise. So adding to the signal conditioning circuit, actually this all circuitry, it will be present. Sorry, this all circuitry, it will be present in my this signal conditioning circuit only, and this smooth sine curve, it will be going to ADC, where I will be performing an conversion to analog to digital, and this digital signal I will be taking to my microcontroller. So in this series, we will be saying that how to choose an ADC. There are lot of ADCs available in market, having different kind of interfaces, and you can get 10-bit ADC, 12-bit ADC. So how to choose one good ADC for our project? And if I talk about my microcontroller, so this full thing we have done on a Pi board, and to give you an idea how it is working on STM32 also, that also I have planned. So going to my next slide, my first question was that why I need a single conditioning circuit. Like you have seen in that, you have seen in this video, so this is a signal conditioning circuit that we have made in our lab. So what is the use of it? Why we want to have a single conditioning circuit? So for that, going back to the PPT. So this is my one current sensor. It is a very good non-invasive current sensor. If I directly check the output of this, that what kind of output we are getting, so you can see that this kind of output we are getting on a DSO. So here you can see lot of noise. I don't want all this noise. I have to remove it. And adding to it, you can see that what is the peak to peak this voltage range. So this is very less. So if like you can see in this current sensor, it is given that corresponding to 60 ampere current, I am getting 1 volt. And you can see that from this DSO measurement, I am getting 374 millivolt. So can you tell that what will be the current level, actual current level? Anyone? I want this lecture to be interactive. Pavan, is my this voice audible?
20 ampere.
2 minutes. Yeah, tell me.
Yeah, Sunil, you are audible.
Yeah, someone told 20 ampere. Come again.
Yeah, 20 ampere.
Yeah, see, so this thing is, if I'm having 60 ampere corresponding to it, I will be getting 1 volt. So it is peak to peak. So if I'm drawing a signal like this, so this peak to peak voltage will be 374 millivolts. So if I want this amplitude, so it will be by 2. 187. So it will be 127 millivolt. If I'm getting 60 ampere corresponding to I'm getting 60 ampere, 1 volt corresponding to 60 ampere, then for 187 millivolt, I will be having 60 by 1000 into 187. So this much will be my this current level. Okay. So my signal conditioning circuit is first work will be to reduce this noise, and the second work will be to amplify this thing, because my this ADC, it will be having I have to take it to the maximum resolution. If I am having one ADC, there will be one reference voltage. Assume that 3.3 volt. If my current if my this signal it is near around to this, then I can get a very good output. So that is the for that reason only I need a single conditioning circuit. So in the single conditioning circuit, first I will be using a very good filter. So this is a standard Salenki low pass filter. So in this series, if you have read in your analog system, first while designing a filter means an analog filter, so you can go for first order. But in first order, you can't get a very good output. So this is a second order silent key low pass filter. So this also can be very good question for your assignment, but okay, leave it. So after solving it, you can get a cutoff frequency of 159 hertz. While you are doing this analysis, you may require border plot, Nyquist plot. So a lot of plots are there. So this is a sample border plot corresponding to this filter. So you can see that after like some this is your 100 hertz. So around 159 hertz, you can see that attenuation begins. This is a practical low pass filter. Actually, a low pass filter, if you are taking an idle one, it may be like this. But after implementing this, you can get a border plot like this. After this, our 159 hertz, you can see the attenuation. So for the single conditioning circuit, this is a filter. Apart from filter, also we have to just implement a lot of things in that circuit. So now you can see that this was my current sensor output, having this much of peak to peak voltage. After passing it through my this signal conditioning circuit, so you can see a very smooth waveform. That to peak to peak has been amplified. Any doubts till this slide?
Sir,
Yeah.
so please show the signal conditioning circuit once again.
You want to see that circuit or that PCB?
No, that circuit.
That circuit I have not included in my this PPT. Only a part of that circuit I have included, because in that circuit I am having differential amplifier, instrumental amplifier. So just a simple low pass filter I have included.
Okay.
Yeah. Yeah. So any questions on this? So any doubt is there, or should I go ahead? Okay. So this is a kind of ADC what we are using. Apart from this, we are having some different ADCs also. If you are choosing ADC, so first you have to see that how many what are the number of bits. Like this is a 12-bit ADC. So like this, we are having 10-bit ADC also. So while choosing this ADC, first thing which I should see that what is the data rate, means maximum sampling frequency. So here it can go up to 128 samples per second to 3.3 kilos samples per second. This is a very good ADC for my work. Depending upon your applications, you have to choose your ADC. Like if you don't want a very high sampling frequency, then why you will go and just you spend money and time of that MCU to just sample each and every bit. So since in my application I want a quite a good number of sampling frequency, since we have to go for signal processing, so I took this one. And you have to just see the what is the supply range. Around 3.3 volt is very good for our work. And this interface will be by I2C. If I just uh, tell you something about ADC, we are having some three kinds of things. Like in some of the microcontrollers, we are having this ADC inbuilt. We don't need to buy one extra. If we are going for like STM32, this is a very good processor. And in this, my ADC comes inbuilt. So there is no tension of how to choosing ADC. But if you are going with a Raspberry Pi board, if I go with Raspberry Pi board, then there is some issue like some ADC. It will having I2C interface, and some of them will be having SPI interface. Can anyone tell me that from both of this interface, which one is having more speed? Any answer?
Is it I2C?
No. That is SPI is more it's having more speed than I2C. While doing this stuff, you will be coming to know that why at what time you will be using I2C and at what time you will be having SPI communication. So okay, that is a different thing. Like if you are going for ADS 1015, you can see that it is having I2C interface. If you are going for some other ADCs, then you will be getting a SPI this communication also. Now I will show you the data sheet also. So in this ADC we are having 4 channels, means at a time you can give 4 analog input. This input it will be going to a multiplexer, and after that it will go going to a programmable this is a programmable gain amplifier. So this will provide gain. So assume that in our this demo we are using only one input, that is this one. And this input, it is coming from a signal conditioning circuit. Okay, first we are having one current sensor. The current sensor is connected to this signal conditioning circuit, and now this is connected to the input of a ADC. So this is my input. Assume that it is having 1 volt. So now I have to amplify it. This is my ADC, and I know that my reference voltage is 3.3 volt. If I will double it also, then also I don't have any problem. So this gain amplifier, I can program it from my microcontroller, and assume that I have programmed it to the double the analog signal. So you can directly get a 2 volt. So this is a very good thing from this ADC. And once it is coming to the 12 volt ADC, this is a reference voltage. It is going to that I2C interface, and here we can connect it to the microcontroller. If I tell you something more about the ADC, let me take you to the data sheet. So here I am having one. There are three ADCs: 1013, 1014, 1015. They are from same family, having some bit changes like number of channels. Like say here we can connect, we can interface two analog channels at a time, and whereas in this 1015 which I was using, we can interface four channels. So this is the interface diagram. As I have told you that already I am only using one channel from this SCL and SDA data line and this clock line. I am interfacing with my this I2C present in my Raspberry Pi board. You can see that this is an experimental test bench. This is a test setup for this three-phase induction motor. So I am from my this current sensor, I am capturing this current signals from one phase. I am taking it to my this signal conditioning board. This signal conditioning board. Once my this signal is okay, this lies my ADC. From ADC, I am getting it to my Raspberry Pi board. So to do all this, we are having different methods to take that data from that our ADC to that our microcontroller. Starting, well, we are having three techniques: polling, interrupt, and direct memory access. Lot of people they go with this polling method. Its advantage is that it is quite easy to implement. If you're going for rapid prototyping, polling method will be very good. But the polling method drawback is that like if you're having lines of code, that CPU will execute line by line by that will be executing line by line, and once the code is image that you have to go and search for that ADC and take that data and come back. So till that time our CPU will be flying idle. It will go, it will take that ADC data and again it will come back, and then it will execute all the codes. So it is too much time consuming. If you don't need a very high sampling frequency, then you can go for this. And after that we are having interrupt based data acquisition. So in this we can trigger a ADC, and then it will start the data conversion and the system that and meanwhile that CPU it will be working to execute its work. And once when the software interrupt like that ADC will be sending that my data conversion is done, then it will come back and it will execute the rest of the process. And the most important is the direct memory access. So this thing I will be discussing in this in my this next slide. So till this PPT, till this slide, anybody is having any doubts? Anyone? Okay, so let me go to the direct memory access. So since this direct memory access, this DMA, this can be explained very well on a STM32 microcontroller rather than PIBoard, because this PIBoard it is having a dual core ARM processor. So better to go for this single core and let us work out. So this is a ARM based CPU. You can assume that we are having 7 master and 7 slaves. So this I got from the data sheet of that microcontroller. In this microcontroller, I am having 7 masters and 7 slaves. So as in this is master 1, master 2, master 3, master 4, master 5, master 6, and master 7. what this direct memory access will do, like in this previous slide, assume that this is our ARM CPU, this is my DMA controller, and this is my ADC, and this is my memory, this is my SRAM. So in this direct memory access, like there are buses. So if I'm going for polling and interrupt method, in this both the method, my ARM CPU will be involved. So it will consume some time. But in this direct memory access, my this ARM CPU, it will not be involved in any way. So my this ADC data, it will directly go through DMA to SRAM. So this is very, very fast. This DMA data acquisition method is very fast. So let us understand that how this DMA is working. So like I told that in many of that microcontroller already that ADC is inbuilt. So assume that my ADC it is already there tied to this APB1. If it is not, and if we are going for some other microcontroller in which my ADC is not there and we are interfacing with it externally, so in that case we can connect it to through I2C, or we can interface it through SPI. So what my this DMA thing will do, that if I'm having one APB1 and to this my ADC is connected. So this is case 1, case 2 and case 3. In case 1, my ADC is directly connected to one APB1 this peripheral, or it is connected through I2C, or it is connected through SPI. So in this thing, my this directly this data will go from here. It will travel to my DMA peripheral one, and it will again come to this memory, and it will be saving to my SRAM. Okay. So for this reason only, my this DMA is very fast. It will not involve any of these R buses. So finally, after running that code on that our Raspberry Pi, we will be getting one .txt file. If I am doing that analysis on my this Jupyter platform, so first I plot that signals which I got from my this Pi board. So you can see that it is a very good sine wave, and this is my current signal. And if I try to plot the FFT, actually this was my this Fourier transform. So I am getting a very good peak at 50 hertz. So any doubts till this slide? If you're having any doubt, then please ask. So if it is okay, then I will give you the assignment. Patisa Pavan.
Yes, Sunil.
So can we give them the assignment?
Yes.
Okay, 2 minutes. So your assignment will be you have to measure what is happening. So your assignment will be you have to measure a 3.3. So something is happening. Just let me go to print only. So you have to measure a 3.3 kilovolt voltage signal, and you have to save it to a Raspberry Pi board. So this will be your assignment. So I want only two things. First thing is how how you will choose this voltage sensor, and what will be your that path flow, your components you are planning to set. Second thing will be your selection of voltage sensor. I want your interface diagram, how you are interfacing it, your ADC selection. So this is your assignment. You have to submit it in 1 hour. So you can start now. Just remember 3.3 kilovolt. It is a very high voltage. So you have to just keep in mind about the safety. You can start.